Hello, everybody. Welcome back. Today, we are going to be doing part two of optimization. So, I'm going to be going over two different optimization problems today. I talked about the steps and some techniques for actually going ahead and solving these types of questions in the last part, in part one. So, if you haven't watched that one, make sure you go watch that one in order to know what are the techniques that we're going to be using in order to solve these problems. So, this is a continuation of part one. All right, so the first question I'm going to answer today is a large bus carries 2,240 passengers daily from Oshawa to Toronto. The cost to ride the bus is $7 per person. Market research shows that 30 fewer people would ride the train, or I guess, is it a train or a bus? Doesn't matter. I guess the train now for 15 cents for each 15 cents increase in fare. If the large bus can transport a maximum of 2,600 passengers daily and carrying fewer than 1,700 passengers means costs exceed revenue, what fare should be charged to give the largest possible revenue? Okay, so first things first for this type of question, let's let X represent the number of price increases. Okay, so if X is positive, that means that's how many increases there were. If X is negative, like if X is -3, that is the opposite. That means there were 3 price decreases. So X can be negative because we can technically have negative price increases to the point where we're actually taking that original $7 cost and we're decreasing the price. So, what are we trying to optimize here? Well, we're trying to optimize the revenue. It says what fare would be charged to give the largest possible revenue. So, revenue is basically money that the bus system makes for this journey, basically. So, how much do they make? Well, excluding taxes, they make the fare price. And how many times they make that? Well, that depends on how many passengers they have. So times the number of passengers, right? If they have 50 passengers, they make the fare price 50 times. If they have 100, they make the fare price 100 times, and so on. So now let's talk about, well, how can we relate that to X? Well, let's start with the fare price. The fare price is $7 plus 15 cents for every X, right? So it's $7 originally, plus it goes 15 cents up for every time we do a price increase, or 15 cents down if we do a price decrease. Now, what about the number of people? Well, originally it's 2,240, but every time we increase the price, we lose 30 people. So basically, we're making a trade off where more people would ride this train or this bus if we decided to make the fare price less, right? But if we make the fare price more, then less people ride the train. Okay, so now what we need to do is optimize the revenue. We want to find out what is the price that should be charged for the maximum revenue. So the next step I'm going to take is I'm actually just going to multiply through here and say that revenue is equal to 15,680 plus 126x minus 4.5x squared by expanding, right, by using the FOIL method. And then I'm going to take the derivative. So the derivative is equal to 126 minus 9x, right? So that's our derivative, okay? Now, in order to maximize the derivative, we're going to set our prime, our derivative, to 0. So that would mean 0 is equal to 126 minus 9x, which means that 9x is equal to 126, which means that x is equal to 14. So therefore, the optimal price involves the fare having 14 price increases. So just a reminder, the fare price we said was 7 plus 0.15 times x, right? And we found out that x is 14. So therefore, the fair price should be $9.10 if we want to maximize our revenue. All right, so what fare should be charged to give the largest possible revenue? It's $9.10. Now, let's say they didn't ask that question, or let's say in addition they asked another question which said, determine what is the largest possible revenue. Then we would just have to put this $9.10 back into the original R. But in this case, we do not actually have to do that because it did not ask us that. What it asked us instead was it just asked what fair price should be charged to give that revenue, not what is the revenue. So therefore, the price that should be charged, the price that should be charged to maximize the revenue, or to max the revenue, is $9.10 per ticket, right? Because that is a big enough number that this company is making quite a decent amount of money for the tickets, but it's not so much that people aren't taking this bus, right? You know, if it's going from all the way from Oshawa to Toronto, I would say that's a pretty good deal. That's a pretty far distance, and you only have to pay $9.10. I bet a lot of people would take that trip, right? Because it's not so much money that people wouldn't take the trip, but it's enough money that, you know, $9.10 per ticket. If they're getting thousands of people per day, they're making a pretty nice chunk of change there, right? That's gonna add up very quickly, which is good. All right, very good. Let's move on to number 2. Number 2 says a cylindrical chemical storage tank with capacity of 1,000 meters cubed is going to be constructed in a warehouse that is 12 meters by 15 meters with a height of 11 meters. The specifications call for the base to be made of sheet steel that costs $100 per meter squared, the top to be made of sheet steel that costs $50 per meter squared, and the wall to be made of sheet steel that costs $80 per meter squared. Okay, so it sounds like the base is going to be the most expensive. It costs $100 per square meter. The top, which I guess if it's a what did it say? A cylindrical storage unit. The bottom and the top, if it's a cylindrical tank, is going to be the same as that, and it's going to cost 50 meters squared. So I guess on average, those two together would be about $75 per meter squared if we take the average. And then the wall is slightly more than that. The wall is $80 per meter squared. And we're wondering what proportions are going to meet those conditions and minimize the cost of steel for construction, right? Because we want to basically pay as little money as possible while still making a storage tank that meets these specifications. And also, we need to also keep in mind here that it's in a warehouse that's 12 meters by 15 meters with a height of 11 meters. So the maximum height of this cylinder can be 11 meters. In fact, actually, it probably have to be a little less than that. But for the sake of argument, let's just say it's 11 meters because they don't really specify how much lower it has to be to actually fit it in. And it's 12 by 15, right? So we know that that circle, it has to be able to fit in this warehouse properly. So that's something we should just check at the end to make sure that it does indeed fit in the warehouse properly. So basically, we have a warehouse and we have our cylinder. So I'm not going to bother drawing the warehouse. I'm just going to draw the cylinder, and we'll just make sure it meets the specifications after. If you wanted, you could also draw the warehouse around it if you wish. I don't feel that that's necessary though. Okay. So in this situation, we know that the volume is what? The volume is pi r squared h, right? That's our volume. And in this case, we were told that our volume is 1,000 meters cubed. So 1,000 is equal to pi r squared h. Now keep in mind pi is just 3.14159 and so on. And so pi is really just a number. So pi is not some quantity we have to figure out. We just have r and h as our unknown variables here. Okay, keep that in mind. So therefore we can argue that h is equal to 1,000 over pi r squared. Now, in this case, could we possibly, solve, and say r equals blah, blah, blah? We could. However, in this situation, it's so much easier to not do that because then we won't have to deal with any square roots. It's much easier to just say h equals blah, blah, blah. Right? So I'm going to do that. It would work if you did it the other way with r, but I am not going to do that. It's going to make this way more complicated than it should be and just take twice or three times as long, perhaps. So I'm not going to do that. I'm going to stick to the path of least resistance here and do it this way. Okay. We know that the surface area is equal to what, right? Because surface area is going to tell us the amount of material we would need. So the surface area is what? The surface area is pi or 2 pi r squared, right? And the reason it's 2 pi r squared is it's because it's pi r squared for the bottom, right? That bottom base, and then also 2 pi r squared for the top, right? So that's how much it's going to be. And then plus 2 pi r h, right? Because 2 pi r is the diameter, or not diameter, sorry. 2 pi r is the circumference around the circle, right? So that circumference times the height, right? Because if we think about it, if you just cut open a cylinder and then, you open it up, it's really a rectangle. And one of the sides of that rectangle is the height of the cylinder. And one of them is the circumference. That full circumference around the circle is the other length. So that's why the surface area equation is the way it is. So if you don't have it memorized, you could try to memorize it, or you could also just remember that explanation and you'll never forget the surface area. I don't have this memorized to this day. I only know it because, I can piece it together as to why that's the equation of the surface area. Now, this is a bit unique though. We don't just want to minimize the surface area because the different parts cost different amounts, right? The cost for the 2 pi r squared is going to be, let's see, so 100 pi r squared for the bottom, for the base, plus 50 pi r squared for the top, plus 80 times 2 pi r h for the other part, right? So we're basically now putting in the prices for the different parts. We're acknowledging the fact that not every bit of material for this is going to cost the same amount. If every bit of material costs the same amount, we would not have to take this step. Rather than minimizing the cost directly, we could just minimize the surface area, because in those situations, minimizing the surface area is the same thing as minimizing the cost. Okay, let's move on. So then the cost would be equal to, we can simplify this further a little bit more, pi r squared plus 160 pi r h. Now we're also going to sub in, actually I should do that at this step and just say that h is equal to 1,000 minus pi r squared. And then we can actually simplify this even further. And we can cancel this out, and we can cancel one of the r's out. So that's going to be plus 160,000 over r, right? Or r to the minus 1 we could even put, because that's going to make it a bit easier for us to take the derivative of, which is undoubtedly our very next step here, okay? So let's set c prime equal to 0. So therefore 0 would be 300 pi r minus 160,000 r to the minus 2, which is the same as over r squared. So what does that mean? Well, that means that 300 pi r is equal to 160,000 over r squared. All right, and then that means that r cubed is equal to 160,000 over 300 pi, right? So we can just type that in our calculator and then take the cube root, right? So r cubed is going to be 169.85 approximately, meaning r is about 5.53 approximately. Okay? All right. Now, what about h? Because they didn't just ask what is r, They asked what proportions meet the conditions that minimize the cost per construction. So we also must find H as well. So we said earlier, H is equal to 1,000 over pi r squared. Now we know that r is 5.53. So H is going to be equal to 10.41. So therefore, to minimize the cost, H should be equal to 10.41 and R should be equal to 5.53. And there we have it. There's our optimization. I know a lot of people find optimization tricky at first, but I do hope that this helped. All right, we'll see everybody for curve sketching, which is our next unit. Bye for now.